Hello everyone, my name is Zuho from Linköping University. So today I'm gonna talk about my contribution for LINK-SIC workshop 2020, and the work is on separation of closed loop sensor and system fault for quadcopter. So to start, we usually have the quadcopter to carry out some kind of outdoor mission, whereas the quadcopter dynamic is significantly affected by external wind, external disturbance, and of course, quadcopter can experience some sensor faults and system faults. So the main goal of the book is to detect any system change in the quadcopter by compensating for sensor fault and regardless the external disturbance. To start, we model the quadcopter by using the translation movement and rotational movement like equation 1. And quadcopter usually have to follow a predefined path. Here in the next plot, you can see the blue line is actual uh, predefined path, and the red curve is the actual position of the quadcopter. The red curve follows the blue curves quite well. So again, the main goal of this work is to detect payload variation of the quadcopter. And to do it, first we need to estimate the gyro bias by using a fixed time window filter. So after obtaining the gyro bias estimate, we can use for the accelerometer bias estimate. In the accelerometer bias estimate, we need another measurement from the GPS, and this estimate is based on a time varying model given in equation 2a and 2b, where is depending on the time varying yaw angle and time varying yaw rate. The input of this model is from IMU, providing the row rate, the pitch rate, the acceleration x, AX and AY given in 200 Hz. And the output of this model is from GPS, providing the absolute position and the absolute velocity at 1 Hz. In the next figure, you can see the sensor fault estimation results. So you can see that just using a fixed time window for gyro bias and the Kalman filter for time varying model for acceleration bias, we can estimate the gyro bias and the acceleration bias quite well. So the next step is to design a chain detector by first we project equation 1 into XY plane in the boric fixed frame to obtain the sensor to sensor model in equation 3, and we use an IV instrumental variable code function for detecting the mass, and the expression of the IV code function is given in equation 4, where there are some important factor like lambda is forgetting factor, the residual R1 and R2 is computing using nominal mass, and given in equation 5. And you can see in the next figure is chain detection results. If we do not compensate for the gyro and accelerometer bias, you can see in the sub plot, it's very difficult to conclude any uh, mass variation of the quadcopter, but by just compensating for the gyro bias and accelerometer bias, the IV code function show very clear mass variation after 40 seconds. So it means that by combining the bias estimate and the chain detection, we can easily detect any payload variation of the quadcopter. And there are two papers. The first, the framework of the whole work is already published in paper number 2 in IFI World Congress 2020, and this new results will be published in the paper number 1. And last but not least, thank you for your attention and bye bye.